Okay, so this is an interesting preprocess. How does this actually help me? Well, let me take a given query. Let's say ACC. To do a search on this, what I can do is I can have one index. I'm going to say low because really, like, I think this is the beginning, this is the end. So I'm going to say the low index is here at the beginning. Let me put it here. Low and high. And then what I can do is actually do essentially a binary search algorithm. I can compute the midpoint and see what side of that does my query exist on. And then I can keep recursing until I find a perfect match of my query, or I run out of, like, my range becomes empty. So what happens with ACC? So I have my low, I have my high. The midpoint is here. ACC is less than CGC, so I should recurse in this upper range. Okay, let me erase these ones. So now I don't have to check CGC anymore because it wasn't a match. So I'm going to make my midpoint, so I'm going to make my high be 1 higher. This was my midpoint, it didn't match. So now this is low, this is high. Again, I check, does this ACC match my mid, which is right in the middle? C does not match ACC. ACC is less than C, so I should recurse in this upper range. Okay. So this is also high, and it's also, when I compute the midpoint, it's also the midpoint because all three of these are equal. So low is here, high was also set to here. The midpoint is the average of them. They're equal, so the midpoint is also the same thing. ACC is less than this. Therefore, I should recurse up. Okay, so I should recurse up. But uh-oh, now I'm out of range. I don't have anything else. So now my range of values is the empty range. So I have failed. ACC does not exist in my query sequence. Let's try another example. My values. Okay, let's try this one. So ATC. So low starts here, high starts here. So ATC, I compute the midpoint. ATC is less than my midpoint. It's less than CGC, so I need to recurse up. Okay, so high will go here. I recursed up. I do it again. Compute the midpoint. ATC is less than C, so I recurse up. High equals mid minus 1. High and low are equal. So then mid is their average, which is also the same value. ATC, hey, that matches. ATC does indeed match the prefix of this suffix. Therefore, yes, ATC exists at index 2. Okay, let's try one more example. Okay, so now we're going to try to find GC. So again, I start with low at the beginning, high at the end. GC I compare against the midpoint. GC is greater than the midpoint. Therefore, I should recurse in this lower range, right? GC is bigger than this, so I recurse in the lower range. So now my low would be here, and I do it again. So the midpoint of low and high is here. I compare my query against my midpoint. Hey, my midpoint matches. Therefore, this is the correct range. Now, what I want to do, now that I've found a midpoint that matches, is I want to tighten my low and my high such that I only contain matches to this. So my low is here. Okay, well, so my low, I would check, does it match my query? Yes, it does. Therefore, low can stay exactly where it is, right? Now my high is greater than my query, so I would want to move it up. I'm going to move up my high. Now my high also matches my query. My high is here, it matches my query. Therefore, high is also at the correct position. Now I'm done. Everything in the range between low and high is a perfect match of my query. So that range is index 5 and index 0, which if I look at this original thing, those are indeed the two indices. Let's think about the time complexity of this algorithm. So first, we did this database preprocessing, which if I have a string of length, so this string is length n, this preprocessing, well, I have to sort big O of n indices, which I can do in big O of n log n. Really, there might be a bit more computation though, because I might have to do a big O of n comparison for each of the comparisons in my sorting algorithm. So really, it's probably more likely to be closer to big O of n squared log n, right? So for example, if I did this comparison, this is a big O of n string, this is also a big O of n string. If I have to do roughly big O of n log n comparisons, where my strings could be big O of n long, overall, in the worst case, it would likely be big O of n squared log n. But keep in mind, this may seem really bad because this is a really large database. N could be as big as 3 billion. But in reality, this is not so bad because I just pre-process this once, and then every future experiment when I have new queries, I just use this existing pre-processed database. Okay, so given the pre-processed database, because I don't have to recompute that, what is the time complexity of doing this search? Well, if my query is length k, if I have big O of n indices, so this is big O of n indices, I do a binary search to find the proper range, which is big O of log n. And during this binary search, I might have to compare k letters. So really, it's more like big O of k log n. K is really tiny, so maybe this is negligible, but regardless. And remember, this is per query sequence. So if I have m query sequences, I would do this for each of my queries. This would become big O of m times k times log n. So we described a search algorithm that's basically just binary search. So given a suffix array, I start with low at the beginning, I start at high at the end, and then I just keep finding the midpoint and then updating low and high, so on and so forth, until eventually I find a midpoint that matches my query. But then once I found that midpoint, I told you we have to then shift low downward and shift high upward to find the first instance and the last instance that matches my query. Instead, what if I just do two different binary searches? So what I could do is a binary search for the low. So I can do one binary search where I start with this range, and then maybe the midpoint is bigger than my query, so then I'll do it in this range, and then maybe my midpoint again is bigger than my query, so I'll do it in this range. Maybe now my midpoint is larger than my query, so then I will do it in this range, so on and so forth. And I would keep doing this binary search until my midpoint, it converges onto a value that I'm looking for, like a value that matches my query, but also that the previous value does not match my query. So for my low, I do a binary search, where I have a match to my query sequence, but I have a mismatch. So my query matches to low, but my query mismatches to low minus 1. Right? So query matches to low, but it mismatches to low minus 1. So my low matches, but the one immediately before it does not match my query. And then similarly, I can do another binary search. I could actually start at low, and then in this range, find a midpoint and see does it match my query. Then and then basically do another binary search looking for the valid high. And really, I would be doing a binary search again. So a second binary search where, again, I want to match my query to high, but I want a mismatch of my query to high plus 1. So in other words, I'm doing a binary search looking not only for a match, but specifically for a match such that immediately after it, I have a mismatch. This will give me my precise range of matches, and all of the indices in this range are my matches to my query sequence. Instead of doing a single binary search, I'm doing 2 binary searches, but still this is big O of log n. Right? This is still big O of log n because I'm doing 2 log n binary searches, but still 2 is just a constant. So big O of log n. Technically, you would have some k term potentially, because technically a mismatch could be big O of k. I can have a scenario where I have a perfect match for all of the big O of k prefix of each of my suffixes, and then I would have to mismatch at the very last one. So technically, I could have a k term here, but really, what I care about is that it's roughly big O of log n. Actually, I'll keep the k there. So yeah, it's big O of roughly log n, potentially times a k term for doing the equality check.